So in this talk, I'm going to talk about Scylla's query paging, how it used to work, what were some of the problems with it, and how we improved it, and what are the effects on, especially on large partition scans. My name is Botond. I'm a software developer at Scylla, and I mostly work on improving the performance of queries. So before we dive into how paging used to work, I'd like to make a brief detour into what paging is. So queries can return an unknown amount of data. The exact amount is only known after the query has been executed. And reading an unknown amount of data into memory, sending it over the network can cause problems. It can fill up your memory or hog the CPU or the network. In extreme cases, it can even cause service denial. So to avoid these problems, Scylla and also Cassandra uses paging. That is, it reads and transmits the results for a query in limited size chunks that we call pages. These pages are limited by the number of rows that they can contain. This is 10,000 by default, but this can be changed by the client. Pages are also limited by size. This is 1 megabyte. This is a fixed limit. It can be changed because setting it to too high values could cause service denial or other problems. So after sending each page to the client, Scylla stops and waits for the client to explicitly request the next page. This is implemented with the help of the paging state, which is a cookie that's sent along with each response to the client. And the client is expected to retransmit it on each page request. This cookie is an opaque binary blob from as far as the client is concerned. It doesn't know about its content. This allows certain flexibility for the server in the implementation of paging. What Scylla used to store in this was just enough information to know where to continue the query from on the next page. That is, it stored the last partition key and the last clustering key, if it was the case. Scylla itself didn't store any state whatsoever. So the state of the query was created anew on the beginning of each page and destroyed at the end. So this query state is an abstract concept that represents all the internal states Scylla has to set up in order to save serve a query. So from Scylla's perspective, each page was like a completely separate query. This had the advantage of simple code, but it had many drawbacks, as we will see. So as I said, the query state was set up anew on each page. This involves a lot of non-trivial work. So this is relatively cheap for a row cache, but it's especially bad for reads that have to go to the disk. Scylla has to identify the SS tables, has to read summary and index files, and then has to skip to the correct position in each of the SS tables. So when this state is was destroyed at the end of each page, all this effort was all lost. Since Scylla doesn't use the OS page cache, this effort was truly lost. Scylla didn't get the benefit of having a warm page cache on the next page. This, of course, the problem scaled with the size of partitions. As with bigger partitions, you have many more pages, and on each page you have to repeat all of this work. So the solution, not surprisingly, is to make paging stateful. Don't be that wasteful. create the the query state only once on the very first page, and use it throughout the entire query. This sounds very simple, but it had many details to get right. So on the end of each page, Scylla saves the query state into a cache using a unique key that's generated on the very first page. The key is persisted using this paging state cookie that I was talking before. And then on each subsequent page, we start by looking up the saved state and then continuing the query where we left off on the previous one. So let's talk about this queries, mysterious query state in more detail. The query has a local state on each shard of each node that's involved in the query. So in this example, in this imaginary cluster that has 3 nodes, each with 6 shards, an imaginary query that runs on shard 1 of node 0 and node 2. This query, the state of this query would be involved of a local state on shard 1 of node 0 and a local state on shard 1 of node 2. We call this local state the Querier, and this is a concrete object that we have in the code. It contains all these states and logic required to serve the query, the part of the query on that particular shard where it lives. So an example query that might look like this is a single partition scan with a CL of 2 that hits these 2 nodes. So all these, the query state is all local to replicas. We don't save, Scylla doesn't save anything on the coordinators themselves. And just to quickly recap, coordinator is the node that receives the request from the client. Its job is to choose the replicas to send the request to, and at the end merge the results that it receives from the replicas and send it back to the client. The replicas are the nodes that actually have the data and that are actually executing queries. So these local states that I was talking before all reside on the replicas. What this means is that if we want to persist the state of the query and reuse it for all of the pages, we have to consistently send each page request to the same replicas. We can't just choose a new set of replicas on each page like we did before. So this is again implemented with the help of this paging state cookie. At the end of the first page, Scylla saves the list of chosen replicas in the paging state. And from then on the beginning of each page, it retrieves this list and then just sticks to these replicas. This has a side effect. So normally drivers will choose coordinators that are also replicas. This is called token-aware driver. Token-aware host selection, but drivers also will rotate the coordinators. So on each page, they will choose a different coordinator for load balancing purposes. So because now we want to stick to the same replicas, it can happen that the driver will choose a coordinator that is not one of the replicas that were in this initial list. And so we will introduce an extra network hop. This can be solved by modifying the drivers to stick to the same coordinator for the entire query. And in fact, my colleague Piotr will talk about this in his talk later this day. So the foundation of stateful query is the Querier cache. The cache where these queriers, these local states on on replicas are saved in. This is a special purpose cache. Each shard of each node has one of these caches. Like I mentioned, the entries are saved under the query key, the unique key that's generated on the first page. And the cache supports multiple entries inserted with the same key. This is necessary because in the case of inquiries, inquiries are select queries that select a list of partitions. It is possible for two listed partitions to be collocated on the same shard of the same node. In this case, there will be two such Querier objects collocated on the same node. The cache has to support saving two or more such Queriers with the same key. In this case, we differentiate between the Queriers by their read range, the partition they are reading. In a perfect world, each lookup for a saved Querier would hit, and we would happily use the Querier to continue the query where we left off. Unfortunately, we don't live in a perfect world, and a lot of things can go wrong in distributed database. A replica that we used for previous pages might become unavailable. The query might have to move to a new replica, which will not have a saved state, and the lookup will miss. In this case, we just create a new state, a new Querier, and continue. There are also cases where although the lookup succeeds, we are not able to reuse the Querier to continue the query. There are several reasons for that. One is if the position the Querier stopped reading from on the last page doesn't match the position where the page request wants to continue reading from. Again, there's a lot of reasons why this can happen. Most obvious one is if nodes have a mismatching data set because some of them missed writes and the last page triggered a read repair. This is one of the cases where the position will be mismatching. Another possible reason is if the replica is not contacted for a few pages and then it is contacted again. For example, because it was very busy and it was unavailable and the query have moved to another replica for a few pages. Another reason for this not being able to reuse the query and having to drop it is schema version mismatch. So it is possible for schema alter statements to be executed concurrently with queries. In this case, it is possible for a page request to find a query that has a schema that's older, that's of an older version than the page request has. In this case, we decided not to try to come up with complicated code to deal with this problem, as it's quite a rare event, so we just drop it and create a new Querier. We want to take care for the Querier cache to not take up unbounded resources. So we have several eviction policies in place. The first one is time-based. Queries can be abandoned. The client might crash, network connections might break up, a number of things can happen. So when we insert a Querier into the cache, we attach a time to live to it. This is 10 seconds. When this expires and the Querier was not looked up in the meanwhile, it is evicted. We also want the memory consumption of the cache to be bounded. So each time we are about to insert a new Querier, we check the memory consumption. If it's above the limit, this limit is currently 4% of the shard's memory. We evict the oldest Queriers to make up space for the new one. Lastly, we have read concurrency control in place for the Queriers. for reads going on any given shard of a node. And this works based on permits. So each read when it starts, or each query when it's created, it has to obtain a permit to start executing. There's a limited number of permits, of course. When the permits are run out, the reads, new reads are just queued up. They can't start executing. Queriers stick to their permit for the entire duration of their lifetime. So they will have the permit even when they're sitting in cache, not doing anything at the moment, to make sure that new reads can progress. When the permits run out, we evict the oldest queriers again from the cache to free up permits. To help diagnose problems around stateful paging, and as well to help observe the effectiveness of it, we added several counters and new trace messages. We added counters for each lookup. We added counters for misses. Misses are lookups that failed. We added counters for drops. Again, drops are lookups that, although succeeded, we found that the query cannot be used to continue the query, so we had to destroy it. From these three metrics, one can derive the cache hit rate. Ideally, this will be 100% or 1, depends on how you calculate it. If you see any of the misses or drops, or especially a large number of them, that might indicate either a bug or some other irregularity in the system. And it might explain a degradation of query performance. We also added counters for all 3 eviction policies that I was talking about. And we have a counter for the current population of the cache. There's also new SQL trace messages. We log each time a query is looked up in the cache and each time a query is cached. In the former case, we also log whether the lookup was successful or not. If it was successful, we will also log whether we were able to reuse it or we had to drop it. If we had to drop it, we will log the reason why we had to drop it. In our benchmarking, we've mostly focused on the use case that was suffering from stateless paging the most. There is large partition scans and range scans that have to go to the disk. So this is the results for single partition scans. This is a normalized graph. So it shows the improvement itself instead of the actual numbers. Before is the result with stateless paging, and after is the result with stateful paging. This was measured with scanning the large partitions for a fixed period of time. So you can see that it's quite a nice improvement in throughput. This is the results for partition range scans. Again, this is a normalized graph. So you can see that the improvement is not quite as nice as for single partition scans. The reason for that is that range scans are a lot more complicated than single partition scans. They have a lot higher CPU cost, and disk is a smaller factor in their performance. I also included the improvement in the disk usage. The improvement in the disk usage is much more significant than the improvement in the throughput. The overall disk is accessed a lot less, and we read a lot less bytes per a single SQL read. So in summary, stateful paging delivers on providing better resource utilization, especially on reducing disk access. It improves the throughput. It improves the handling of large partitions, which was for a long time a pain. And it's especially beneficial for disk-bound setups. We published 2 blog posts with a lot more details on how all this is implemented. So if you're interested in more details, I recommend you go ahead and read them. But even if you're not interested in more details in paging, I don't blame you. You can. I still recommend visiting our blog, which has a lot more interesting posts and interesting topics. So this concludes my presentations. Thank you.